All right, welcome back to The Explainer. Today, we're diving into something really cool. How to translate the silent language of a plant into the pure, cold logic of code. We're going to take a living thing and turn it into a program, all to answer one surprisingly tricky question. So, how do you actually ask a plant if it's thirsty? I mean, it sounds simple, right? But plants can't just tell you. They show you, with wilting leaves, maybe some stunted growth. But here's the problem. By the time you see those signs, the damage is already done. So what if we could figure out exactly what a plant needs way before it even starts to get stressed? Well, that's exactly where this idea of a digital twin comes in. And this isn't just some static, boring model. No, we're talking about a dynamic simulation that basically lives and breathes right alongside the real plant, predicting its every need in real time. It's an awesome concept. But, how do you even begin to build something like that? First things first, a plant's thirst isn't a simple, fixed thing. It changes all the time, right? It depends on the weather, the time of day, even where it is in its life cycle. So trying to predict that need, well, it means you've got to understand a really dynamic system. And that's exactly why a detailed model is so absolutely essential. Okay, so let's think about this digital plant like we're cooking something. It's a really complex recipe. And to get the final dish just right, which in our case is a perfect prediction of thirst, we first have to get all our ingredients together. In the world of programming, these ingredients are basically all the variables that define our plant and the world it lives in. So, in coding, we don't call them ingredients, we call them parameters. You can think of them as all the little knobs and dials we can turn to perfectly describe a specific plant, say a head of lettuce growing in a specific place. Now, there are dozens of these parameters, but don't worry, they all kind of fall into three main buckets. First up, you've got your environmental factors, basically the weather and the world around the plant. Then there are the plant traits. This is the unique blueprint of the plant itself, things like leaf size. And finally, and this is super interesting, it's internal plumbing, all the hidden mechanics of how water actually gets from the roots all the way up to the leaves. All right, so we've got our ingredients list, our parameters. Now, our model uses two totally different but complementary recipes to figure out how thirsty the plant is. One looks at the problem from the outside in, and the other from the inside out. Let's kick things off with that first one. This first recipe, it's all about the environment. The model uses a function, and the name kind of gives it away. It's called Calculate Realistic Water Uptake. And what it's really doing is asking a simple question. Okay, looking at the weather today, how much water is this plant supposed to be losing to the air? And to answer that question, the code has to focus on one absolutely critical environmental factor, vapor pressure deficit, or VPD for short. You can just think of VPD as a measure of how thirsty the atmosphere itself is. It's all calculated from temperature and humidity, and it is the single biggest force that's pulling water out of a plant's leaves. So think of it this way. A high VPD means the air is super thirsty. It's literally yanking moisture out of the plant's leaves. That whole process is called transpiration. On the flip side, a low VPD means the air is already pretty humid, so that pulling force is way, way weaker. So how does the code actually turn all this into a number? Well, it uses a process that's based on a famous and pretty complex equation called the Penman-Monteith equation. But let's just break it down into simple steps. First, it figures out a baseline water loss for the environment. That's our ET0. Then it multiplies that by something called the crop coefficient, or KC, to make it specific to our plant, lettuce in this case. And finally, it fine-tunes that number using things like temperature and that VPD we just talked about. And voila, the result is the crop evapotranspiration, or ETC, the plant's predicted water use for that day. Okay, on to recipe number 2. This one flips the script. Instead of looking at the atmosphere, it looks inside the plant. It uses a different function called Calculate Hydraulic Water Uptake. And this time the question is, forget the weather for a second, how much water can the plant's internal plumbing actually move from the roots to the leaves? And at its heart, this calculation is all about a basic law of physics. It's a lot like Ohm's law, if you're familiar with electricity. The flow of water is just the pressure difference, that's the push from the soil to the leaves, divided by the resistance of the plant's pipes. It's simple, right? A bigger push or less resistance means more water can get through. So where does that resistance come from? Well, it's mainly from two spots, and you can just imagine them as two pipes hooked together. First, there's the root conductance. That's how easily water gets into the plant from the soil. Then you've got these xylem conductants, which is how easily it travels up the stem. And just like with real pipes, the total flow can never be faster than the narrowest part of the system. But what happens if those pipes get a blockage? Because under really extreme stress, something mad can happen. A tiny air bubble called a cavitation can actually form inside the xylem. And the xylem, remember, are the tubes that carry the water. And this is a really big deal. A cavitation is basically like a heart attack for the plant's plumbing. It can severely block the flow of water. So of course, our model has to account for this. It uses a parameter called the cavitation threshold to keep an eye out for it. If the model sees that the internal water pressure is dropping too low, it simulates this blockage, and that automatically reduces the plant's ability to pull up more water. So there you have it. We've got our ingredients, all those parameters. We've got our 2 different recipes for figuring out thirst. Now let's bring it all together and see how the code actually builds our final digital lettuce. And here's the magic. This line is pulled straight from the source code. There's a function called create lettuce water uptake model, and it does exactly what it says. It takes all those parameters we just went through, pulls them from a config file, and builds a complete, totally customized model that's ready to start making predictions. So what's the big takeaway here? What does all this actually do? Well, by combining the atmospheric demand for water with the plant's physical capacity to supply it, this digital twin creates a complete picture of the plant's needs. And it's not just some fixed number. It's a living, breathing prediction that changes as the plant grows and the weather shifts. For things like precision hydroponics, this is a total game changer. It means you can deliver the exact amount of water a plant needs, when it needs it. That means less waste and much healthier plants. And that leaves us with a pretty fascinating thought, doesn't it? We've essentially built a translator for a plant's thirst. By turning biology into code, we're paving the way for hyper-efficient farms. And it really makes you wonder, what other silent conversations happening in nature are just waiting for the right algorithm to come along and decode them? What does the farm of the future even look like when literally everything can be digitized?